Hello, everybody. So what we're going to be doing today is we're going to be looking at zyBooks. So in week 11, there is this video, week 11, lecture 1, and that covers looking at it up to some sections like 6.5. Maybe you can read that in there. What we're going to be doing today is we're going to be looking at the rest of this, which a lot of it is stuff that we already know from the labs that we've done on this stuff. But also, I'll go back to all the way to 6.1 to explain some of the stuff on gates. So, with that said, I think we'll go ahead and get started here. So, I think I have notes up. Yeah. So, to start with, like section 6.1, gates. Couple things I would like to point out. So first thing to point out is like the way that this works is here's kind of the key to the whole thing. We'll look at it before we look at it. When you look at the, let's say, circuit or a gate, what's a gate? Like AND gate, NOR gate. I don't know why I said NOR. And or NOR and whatever it is, it doesn't really matter. Whenever you look at those gates, there will be transistors. Okay. And some of those transistors, and it'll make more sense when we see the diagram, some of those transistors have a circle, right? A little O on it. Um, and we know from when we learned about the circuit diagrams that the O means not, right? Like a little circle. They draw a little circle to indicate not. And that's kind of what it means here too as well. So if you see a circle, so the transistor with a little circle, right, O again, um, will conduct if the input is a 0. The transistors without the little circle will conduct when the input is a 1. So I'm trying to write this before we look at it. And so like think about it before we look at the diagrams. So if the transistor has a little circle on it, then that means conducts electricity if the input is 0. If there's no little circle, that means conduct when the input is a 1. Okay? So keep that in your head. So let's look at 6.1 now with that in mind. So here's two little diagrams. And so this is a transistor and this is a transistor. So we have transistors here. And one of them has this little circle on it and the other one does not have the little circle on it. And so if you look, the input is here, the A is 0. And so based on what we said in the note here, if there's a little circle, then that should conduct if the input is 0. So here's the little circle, here's the input 0, and because of that, this one will conduct, which means if there's a 1 here, high voltage, the high voltage will make it through, and the result will also be high voltage. And on this end, this symbol is for ground, which we indicate as a 0, low voltage. Then because the input is 0, the one without the circle does not conduct, right? Because we said the transistor without the circle will conduct when the input is a 1. So if the input is a 0, the one without the circle does not conduct. And so which one conducts here is the question. And if you know which one conducts, you'll know whether a 1 makes it through, so like a 1 makes it to the output, or you'll know if the 0 makes it to the output. So you have a high voltage, a low voltage, and then the input. Okay. Now over here, you have, the same picture, but they changed the input. So the way you look at this is you say, what's the input? The input is 1. And then so which one conducts? The one without the circle or the one with the circle or the one without the circle? Well, if it's a one, the one that conducts is the one without the circle, which is down here. And so they have that connected to low voltage. So it lets the low voltage through, which, we represent as a zero. So low voltage is zero and the high voltage is one. Um, so that's kind of the whole key to working through those. So if you look at a more complicated diagram, like this one right here, let me find my notes again. Where are they? Here. So if you look at this diagram right here, and they're giving you an A and a B, and there's a Y here, right? So like if you just think about this, just in this diagram, if A is zero, for example, and B is zero, right, then what happens? Just thinking our way through it. Now they have ones labeled here, but I'm saying let's put zeros mentally. So forget the ones that they have. We're putting zeros. So if you think about it, there's an A there, there's an A there, there's a B there, there's a not B there. There's a lot of stuff going on, right? So we have to think about each section. So if A is zero, right? So forget this one. If A is zero, then that means the one with the little circle conducts. Okay. So if this conducts, then this one will make it through this side and will end up over here. So in that top group, uh, A equals zero makes this conduct and the one makes it through here. So this is not the red line we're dealing with, right? Because I changed the input. So the zero comes through here and ends up here. Or sorry, I say the zero doesn't do that. A is zero, which means the one makes it through on this side and ends up here. So with A equals zero, B equals zero, where this zero is, we actually have a one. And the top group, A1, is let through, I'll say. It lets through the higher voltage. Okay. So then this is a one. And then if this is a one, well, there's a circle up here. There's no circle down here. According to our instructions here, if there's a little circle, it conducts if the input is zero. If there's no little circle, it conducts when the input is one. So if this were a one, not a zero like it says, if this were a one, then this up here would not conduct. This down here would conduct. And since there's a zero low voltage here, it would let the zero through, and the final output would be zero. So in the next section, so the section on the right, the input would be one, which means the bottom transistor, this is not wide enough, or rather too wide. This means the bottom transistor would conduct, right? The one without the circle, which would mean the ground voltage, the low voltage, makes it to the output. Okay. And so that's what you have to do. Now they've drawn the arrows the other way. So if we look at theirs, where the inputs are one, so essentially what this is a diagram of is the last row. So when they did A equals one, B equals one, then if you think about it that way, if A is one, this does not conduct, right? Because it's got the circle on it. If B is one, this does not conduct because it's got the circle on it. So this entire top section does not conduct. But if you look at the bottom section here, if A is one and B is one, then because B is one, this conducts. Because A is one, this conducts. So the zero makes it through this section and ends up here. Then if you have a zero here, Well, this one has no circle, this one has a circle. So the one with the circle would conduct when the input is 0. So the one with the circle conducts, which lets the 1 through the gate into the output. So when you have a 1 and a 1, you end up with a 1. If you had a 0 and a 0, we ended up with, as we worked that out, a 0 at the end. So that's what you have to do for those with the circuit diagrams. And we didn't do this last time. I think I sort of remember this where we just skipped through it by clicking randomly, but we don't have to do it that way. We could actually work this out. Um, I wish I had, actually, maybe we'll do that. Hold on. I'm going to pause this and see if I can open up an image editor. Pause recording. Okay, unpause recording. So hopefully that worked. So like on this exercise here, where this is supposed to be an AND gate, so they're kind of telling you the final answer here. They make you walk through this for an input of A equals 0, B equals 0. So I'm going to jump over to an image editor here, and let's think about what would happen. So we're assuming that the A is 0, the B is 0, the A is 0, and the B is 0, right? So we want to think about what the result is there. So if the A is 0, then this should conduct, right? So if A is 0, then the one with the circle should conduct. So that means the electricity can make it through this side. Okay, so that means a 1 can make it through H. So it says, does H conduct? Yes. Okay. What's the next one? I guess we're filling out all the letters. Okay. So then if we go down here, uh, if A is 0, still A is 0, then there's no little circle here, right? So this should not conduct. So if it's a 0, you need a little circle to conduct. So if it's 0, this does not conduct. I should write no. And then B is 0 as well. So B is 0. So there's no little circle here. So this should also not conduct. No. Oops. Web browser. There. So does I conduct? No. Then we got to figure out J. Well, we already figured out J because if H conducts here, right? Because A is 0, so the one with the little circle conducts, so the 1 comes through here. Then if the 1 comes through here, it's connected to this wire, then we end up with a 1 right here because this one makes it all the way through. Now, we didn't even look at this side, but technically because B was 0, this also conducts, which means the 1 also could have come from this side. Doesn't really matter. The point is that it makes it through. So the 1 makes it through this section and ends up over here. So there's a 1 here. So then you look at this section. So you have a 1. So which one will conduct? The one without the circle? Sorry, the one with the circle or the one without? Well, if it's a 1, this one should conduct down here. This one should not. So this one, no. No. But this one should conduct, which means this value is going to make it through here because it conducts and going to end up over here at the K. So since this one conducts, a 0 makes it through here and we end up with the 0 at the end. So the K should be 0. So K is 0, right? And then they make us do this all again with A equals 1, B equals 0. So if we back this all up, I don't remember what it said. A is 1, B is 0. So if A is 1 and B is 0, A is 1 and B is 0, what happens? So in the top section up here, if A is 1 and this has a little circle, that one does not conduct. But if B is 0, this one does conduct. So a 1 makes it down here like that. Now you can check this bottom section, but here, if B is 0 and this has no little circle, then this does not conduct. So the 0 does not make it through here. only the 1 makes it through here. So if the 1 makes it through here, then this should be a 1, right? I'm going to draw a 1. That's a 1. So you end up with a 1 here. And then if a 1 is here, which one conducts, the top one or the bottom one? Well, this one would conduct if there was a 0 here, but it's a 1. So this one, no. But there's a 1. This one does conduct. So this 0 makes it through here. And then we end up with the 0 at the end. So what does that tell us? We should be able to answer all the questions. So it says J is here. 1. J is 1. If A is 1, B is 0, then K is K 0. And then if A is 1, B is 1, then K is, well, we have to redo it, right? So if A and B are both 1s, back it all up again. So what is 1, 1? Yeah, 1, 1, 1, 1. So if this is a 1 and this has a circle, no conduct. If this is a 1 and this has a circle, no conduct. Down here, though, if this is a 0, no, sorry. If B is a 1, then this conducts. This one conducts. And if A is a 1, then this one conducts. So both of these conduct, which means this 0 can make it all the way through here, over here, and we get a 0 there. Now, if you have a 0 here where J is, then this one up here will conduct, right? Because if it's a 0, the one with the circle conducts. So this one conducts, and this one doesn't. And so if this one conducts, then the 1 makes it through here, and we end up with a 1 where the K is. Okay? And that's kind of what you got to do on those circuit diagrams. So they're not hard, really. You just have to this idea that we said here, right? So if there's a little circle on the transistor, then that means it will conduct when you input a 0. And if there's no little circle on the transistor, then that means it conducts when the input is 1. And so they all have 3 pins, the transistor. So you have the input, and then you have basically low voltage, right, which is 0, and high voltage, which is 1. So there's a high and low voltage, a 0 and a 1, but then the input decides whether the output is going to be low or high voltage. And so if you look at transistor, transistor, or transistor, right? So then you'll see so you'll see a transistor. You can look them up and read about them. So voltage or current is applied to one pair of the transistor's terminals, controls the current through another pair of terminals. Because the controlled output power can be higher than the input power, transistor can amplify a signal, blah, blah, blah. All right. So anyway, those are transistors. So we come back to our work, then hopefully that'll make sense. I know you can just click through it, but you could also pay attention to this. Now, having said all that, I think we can jump now to a later section where I think we did up to like 6.5 is what I saw at the end of the other video, I think. So if we look at 6.6, this is all stuff that we covered in lab previously, but I just want to go through some of the exercises here. So sum of products. So when they say sum of products, all they're talking about is I mean it's literally what it says. So sum of products. So product, right? That's like this, like XYZ or X, X, Y prime Z or whatever, right? Those are products because they're written as multiplied, right? So if you had a sum of products, what would that look like? It would just like terms like these multiplied together. So that'd be like XY plus Y prime Z plus uh X Z, whatever, right? Like something like this. That's a sum of products. Each term is a product, and we're writing them with sums. So, what's a product term? That's a product term. That's a product term. This is not a product term. This is two product terms. So, that's not a product term. A, you could think of an A by itself as being a product term. All right. Now, what sum of products? Yeah, that's exactly what we were just looking at, right? That's a sum of products. That's a sum of products. That's a sum of products. This is just a product, but you could still think of that as a sum of products. You could still think of a single variable as being a sum of products. This is not, right? This is not a sum of products. This is a product of a sum, not what we were talking about. This is also a product of two sums. That's different. So that is not a sum of products. Okay. All righty. Now, they're just trying to get across this idea here that when you do this, right, the product terms are connected with ands and the sums are ors. So we've seen structures that looked like this when you were trying to write a circuit for the things that we've done before, right? So when you look at this, right, here's a simple one. F, G with an or. So that's F or G. So that's F plus G. So this one is the last one. If you look at the next simplest, maybe this one. So this is F, G, and an and. So that's a and remember is written with multiplication. So this is FG. The top is FG. Actually, just from that, I can tell that it's got to be this one, right? Because none of the others have an FG. So this must be B. B must be the top one. If we look at, let's say A, this is an and we have E, F, G all going to an and. So it must be this one. So that was A. A must be this one because it has an EFG. And by the process of elimination, C must be this one. But you can also see on C that, like, for example, you have E and F going to not and an and. So that's not E, not F. And you can see not E, not F. And also here you can see the E comes down and the F comes down. So that's an EF. So, of course, it still makes sense that that's correct there. So, let's see. What are we doing here? This is a animation, so I think they're just gonna, what are they gonna do? Multiply this out? Yeah, they foiled it out, which is valid. Distributive law works for these. And then once it was written this way, then they could draw the circuit. Okay. I mean, they could have also drawn the original circuit. All right. So these are like the basic Boolean algebra rules, right? So if you were to multiply this out and simplify, like A times B is AB, and then A times B not C. So I guess the plus question mark would be A, the apostrophe C, right? So they're just seeing if we can do the distributive law. So CA is AC, and then C times B is CB, or I think probably BC is what they want. They might want it in alphabetical order. They sometimes do. Yeah, so they say. So if you did AB times CD, C plus D. AB times C is ABC. AB times D is ABD. All right. ACB is ABC, and then AC times A. Oh, so if you did AC times A, that would be AAC. But this is A and C. So if you look at the rules that we had a million years ago for Boolean algebra, like A and A is just A. So you don't need an extra A. Okay, what about here? So let's see. They've got this term which needed to be multiplied out. So C times B is BC. Okay. C times AB prime C is AB prime C. And then they say, what's the question mark? Isn't that's just the A, right? Okay. Not A, B is not A, B, and then not A, not B, C. That's going to be not A, not B, C. So we're still just distributing very simply here. Um, I was going to skip this one, but then I saw it slightly interesting. So if you do this, you'd have to like FOIL, right? So you'd have to have not A times C, which is right there. You'd have to have the not A times D, which is right there. But then the B would also have to be multiplied by these two. So you'd have to do the B times the C. And then you'd also have to do the B times the D. So feel like you're back in algebra one, right? I'm not gonna do all this here, but this is like a complicated thing. Um, so there's logic here. It says interrupt logic, and it says how many inputs does the interrupt logic component have? So here's the interrupt logic component. So we're just counting how many inputs it has. So 1, 2, 3, 4, 5, 5, 6, 7. Right? 5 up here, 2 down here. Looks like seven inputs. That's what I saw. How many outputs does it have? So how many arrows leave it? Looks like just one arrow leaves it. So that's just one. Did the designer originally capture the interrupt logic's behavior as a sum of products equation? So let's see here. So if this is what they had first, this first line for R is not sum of products, right? So they didn't start with sum of products, but afterwards they came up with it in sum of products. So the second one is sum of products, but the top one isn't. So I guess they did not have that at the beginning. How many product terms are in the sum of products form? So this is just kind of checking if we can understand where that is, right? So you have to look at this and understand that this is sum of products, and then you just count how many there are. One product, two product, three product, four product, five products. So we just count the terms. Oops, five. How many AND gates are in the interrupts logic circuit? So these two things are ANDed, 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 these two things are ANDed. So that's an AND gate, an AND gate, an AND gate, an AND gate, an AND gate. So that's 1, 2, 3, 4, 5. Oh, also, right below here is the picture. One AND gate, 2, 3, 4, 5. So they drew 5 AND gates as well. So you could count them from the picture also. Cool. So these are not so bad, right? So these are just doing the same exercises that we just looked at. So like C times B is BC, C times not A is not AC, but they want it alphabetical order probably. Oh, it says it right there. So C not A is not AC. Let's skip to the third one. A plus this thing, and then they have A plus. So we got to multiply out the highlighted part. So it's going to be not A, CD. And then we're going to have not B, CD. And these are so close to regular algebra rules that you should have no trouble with these, I hope. Um, let's go to the next section. Sum of min terms. Um, so those min terms are basically going to be the products from the previous section. Okay. So different equations may represent the same function, like a plus b and a plus not ab is the same function. Sameness is not obvious. So standard equation is desirable. So a canonical form of a Boolean expression is a standard equation. Okay. Sum of min terms form is canonical form. Right-hand expression is a sum of products, with each product a unique min term. So um, a literal is a variable appearance. Okay. So is that three variables or three literals? Yeah, because it's three variables, right? So yeah. Does A not B C have four literals? No, right? A, B, C, it's three. Is B not C a product? Yeah. Is B not C a min term? Yeah. Not every product term is a min term. Okay. Min term is a product term having exactly one literal for every function variable. Okay, fair enough. Um, the reason I marked that as yes, because they want us to write our stuff as sum of min terms usually. And if you simplify as much as possible, you are going to have variables disappear, right? So, um, yeah, I thought that's what they were going to be heading towards. But they say no, they say every variable appears once, so that's not a min term. Is A not B C a min term? Yeah. Is A B plus not C a min term? No, because the min terms they said were products, right? Okay. So sum of min terms? Yeah. Sum of min terms? No, right? Because the first term here is missing a variable, missing the C. So this is not sum of min terms. Sum of min terms? No, that's not even a sum of products. Sum of min terms? Yep. Sum of min terms? Nope, missing the B. Sum of min terms? Yes. They didn't write this one in alphabetical order, but that shouldn't matter, right? ABC plus ABC. Did they say anything about repeating, right? We'd have to check their rules here. Um, right side expression is a sum of products with each product unique min term. So those are not unique. So that's no. All right. So interesting. So this is a specific algebra rule that we did not actually use in the lab. So in the lab, we kind of actually we looked at this sort of thing, and we in lab said there was actually a rule that said we could do this. Oh, just let me paste it normally. Okay. Weird. Color is weird. Anyway, we had a rule that actually said in lab that we could take this and I think actually just cancel out that A and make this B plus not A when we were simplifying things. But that's not what they're doing here. This is a different thing. They're saying this is not a min term, right? This is not a min term because it's missing the B. And what it says up here is for any of them that's missing, you can just multiply by like V or not V for whatever term is missing. Because if you think about it, let me just rewrite this. I know that they have to work right there, but make bigger. Um, so if you think about it, uh, if you just took this right here and you wrote B or not B, that would be identical, right? Because B or not B is just one. Because if B is one, then not B is zero, and this is one or zero, which is one. But if B is zero, then not B is one. And so this is still zero or one, which is one. So no matter what, this part that's highlighted is one. So this is like multiplying by one, which is allowed. You're not doing anything. So they're saying because the B is missing, you add this B or not B, and then you would be able just to multiply this out now. Not A, B would be not A, B. And then not A, not B would be not A, not, not B. And there would be your sum of min terms. So this is not sum of min terms, but this one is sum of min terms. Okay, so they're giving you this rule for how to do this algebra here. And then they're giving you more samples here. I want to go find a well, maybe we'll do one of these. I was going to say let's find a challenge activity, but sometimes these ones are a little tricky. So let's do one of these first. So it says we're transforming y equals ab plus not a to min terms. So we would start with ab plus not a, which is right here. Then our next step would be, is this the same one we just did? Our next one would be, that'd be the same thing as if you multiplied by one, like that, right? But then the one is actually, you could write as B or not B. And then after you FOIL that out, you get that. So that's what they're doing here. So for a more complicated one, um, y equals a plus c times b, you would start with that. So let's find it. There it is. Then what you would do is multiply it all out. So if you multiply this out, you'll get AB, CB, which I see here. From there, the first one is missing a C, and the second one is missing an A. So they both need to be multiplied by one, which I see here. Then on the first one, we should replace the one with C plus not C. And on this one, we should replace with A or not A, which I see here. Then this should just all be multiplied out. So if we multiply it out, we'll get A, B, C, A, B, not C. So two terms. And this will give us A, B, C, and B, C, not A. So you get four terms, two when you multiply this out, two when you multiply this out. But then if you look at it, we notice that there's an ABC and an ABC, and you don't need to write it twice because it's this or this or this or this, right? So you don't need to say ABC or ABC. That's redundant. So there you go. Get rid of the duplicate. Cool. So on these, we're filling them in. So it's the same thing. Not AB, not AB times one, not AB times C plus not C. And then if you FOIL it, not A, B, C, and then you have not A, B, not C. So that'd be not A, B, not C. And that's probably plenty. So you could determine if two equations represent the same function by writing them as sum of min terms, right? Because if you write them as sum of min terms and they're the same, then they must be the same, right? So if you wanted to know if this y equals a plus not ab and this y equals a plus b are the same, which there is, right? This was an identity that we covered. Um, the way you could tell if they're the same or prove that they're the same is if you go through the steps of writing them as sum of min terms, then the sum of min terms would have to be identical, which they are, so that if the min terms are identical, then the original thing is identical. All righty. What the heck? Compact function notation represents each min term by a number. Uh, A not B, A not B C is 1 if A, B, C are 1, 0, 1. Uh, oh, okay. So what they're saying here is this. Take a look at this. If you represent, if a variable like, hold on, A, no, you fill that in automatically. So let me type. Okay. So um, if A is 1, you'd get a 1. If you had not A, that'd be a 0, right? And if you had B, that would be a 1. And if you had not B, 0. C would be a 1. Not C would be a 0. Okay. So if you have something like this, let me just undo that and paste it again, where it's not B, right? You could write that you have A, not B, C. So you could write that as 1, 0, 1. But as a binary number, isn't that 5? Because we have the ones place, the twos place, and the fours place. So this is 4 plus 1, which is 5. So they're saying you could say that A not B C is 1, 0, 1, and 1, 0, 1 is 5. So we can call that M5 if we don't want to write it all out. Okay. So like this right here. So you just think about binary numbers when you're doing this, and it should be okay. So like let's see, just gonna try to get higher in here. Right. So this one right here, not A, B, not C. So not A, B, not C. So what number is that? Right? 0, 1, 0 is 2. So this should be M2 if we did that right. Next one, not A, not B, not C. That is 0, 0, 0, which of course is 0. What? It floated back. This one, not A, not B, C. That's 1. 1, 0, 1, right? That the next one is 1, 0, 1. And the last one is 1, 1, 0. So 1, 0, 1 is 5, and 1, 1, 0 is 6, right? 4 plus 2. So the last two are 5 and 6. Cool. So if we were figuring this out this way, uh, what would this be? Cannot determine. Well, we can definitely determine, right? It says cannot determine. So ABC would be 1, 1, 1, right? 111 would be 4 plus 2 plus 1, which would be 7. So 111 would be 7. So it's automatically got to be this one if any of them are right. And then this would be 011, which is 3. So that one. Ah, now here it says if f of ABC is AB, the compact notation is what? Well, they're being sneaky here, right? Because they gave you AB, and what they wanted you to do, so this is wrong. What they were trying to trick you into doing is saying uh, that AB is 1, 1, which is 3. So you'd select M3, but that's not right because AB is actually, stop. Why does it keep filling in ones? AB is actually AB C plus not C, right? Because the C is there even if we don't write it, which is ABC plus AB not C, which is ABC is 111 and AB not C is 110, which is, stop adding, M7 for the first one, because 111 is 7, and then this one is a 4 and a 2, which is 6. So it should be a 6 and a 7. So they tricked you by not writing it in the sum of min terms form. Um, okay, cool. And then here we got algebra rules. Now we've done a fair amount of this in lab, I think, right? So uh, what are we doing here? Okay, expand WX into sum of min terms. Okay, so if you started with a WX, um, is that filled in or do I have to fill it in? I think we need to multiply by 1, right? So let's look for that. Um, okay, yeah, we're going that way. So I'm gonna undo that if I can. Okay, well, I don't know how to make it do it again. I'm gonna reload all the way down here. Wait, yeah, we'll try it. This is a different one. So I think what we have to do is we this is missing the z term, right? So we need to add a 1, which I think starts here and goes here. So I'll click on the right-hand side, and then it says select A from the A here. So I would select this and then apply the property. And now I've got x, y prime times 1. Then what we would need to do is replace the 1 with, it would need to be z plus not z, right? Because this is missing the z, so we need to get the z's involved. So let's figure out how to do that. So I think we would actually need this rule, right? But backwards, we need to change the 1 into a plus not a. So I click the 1, and it says select 1, so I click the 1. And then which one do we want? The x's, the y's, or the z's? Well, we want the z's, right? That's what's missing. So we'll click the z. So now we're here. And then we need to FOIL this out, multiply it out. So we need the distributive law, and we need this distributive law, and we're multiplying it out. So we'll start with the right side and end up with the left side. So we click the right side, and then it says select the A from A times B plus C. So the A is the part outside the parentheses. So I have to click the X and the Y, not Y. Then click next. And then it says select the B, that'd just be Z. Next. Oh. And then I click that and then click apply property. And then we got there. Whew. Complicated. Let's try the third one. Whoa. All right. So should be relatively straightforward. These are both missing a Z, right? So we're basically doing the exact same thing we did in the last one, but we have to do it twice. So We'll do it quicker this time, right? So they both need this one property. So I'll click here, and then it doesn't really matter which one we start with first. So I'll start with this one. So I have to click both of these and hit apply. I'm gonna do it again. I'm gonna do it to this other one. So now they both have a one. Then I need to turn that one into z plus not z and the other one into z plus not z. So that's this bottom property again. So I'll click the one and it says click select the one. I want to turn it into z or not z. Let's do it again to the other one. So I click the one again, click the one, z or not z. So we're here. Both of these need to be FOILed out. So they both need this distributive property. So I'll click the right side of the distributive property and it says A from the A, B plus C. So both of these need to be selected and you click next. Then it says the B, which is the first term here. So I click the first term, next. Now it says the C from A plus B or not, or A plus B plus C. So that's the third term and then apply. And now we got to do it again to the other one. So that's same property. Select the A, which is the thing outside the parentheses, both of them, select. Then the B, which is this first one, next. And then the C, which is the third term, and then apply. And we got it with a lot of extra parentheses. Cool. All right. And then they want us to do some stuff here, similar things. So if we were trying to do A not B to this, we would replace the A not B with C plus not C. I think that's all they want. They skip the step where you fill in the one. Let's go to the third one. What would you do here? It's A, B, C, right? So if we were going to do this and they just want the final answer, then, you'd go there. Whoa. So what would you do? What I would do, well, apparently I would undo is what I would do. I was trying to select this and I'm going to just make it bigger to easier to see. All right. So the first term is missing B plus not B. And the third term is missing C plus not C, right? So we add the missing term in. Then we FOIL them out each individually. So this is going to be A, C, B, which is A, B, C. And then we have A, C, not B, which is A, not B, C. And then this term is going to be not A, not B, C, not A, uh, not B, C, and then not A, not B, not C, not A, not B, not C. So those are the terms. And then there's some rule about this. Use the true form of the literal first when expanding. Enter the minterms in the order presented. The order presented in the equation. What? I don't know what the order presented in the equation is. Okay, we got it. I mean, this is what we got, not trying to change the order of anything. So it worked. All right. Um, what is this teaching us? Decimal and binary numbers. Why is this coming now? That's a question I have. What binary number comes next? After 000 comes 1. What comes after 1? 2. What's 2? This is 2. After 3, right? This is 1 and 2 is 3. Comes 4. What's 4 look like? This one. This is 0, or sorry, 1's place, 2's place, 4's place. So this is 4. After 4 comes 5, which is this one. This is 5. After 5 comes 6, which is this one. All right. Can you count from 0 to 7 in 20 seconds? Yes, I can count to 7 in 20 seconds. Can you? Are we timed? Oh, I think this is timing us and I'm talking. 0. Next. 1. Next. 2. Next. 3. Next. 4. Next. 5. Next. 6. Next. 7. Did it time us? Hey, I wanted it to time us. I mean, we talked rather than doing it, but interesting. Alrighty. We've already talked about, I think, converting from binary to decimal and decimal to binary. But if you are doing this, like you might want to actually just use this to help you, right? So like, what is 001? It is 1. What is 0010? It's 2, but if you don't know that, right, you can use the little applet up here to help, right? 0111 is 7, but you can use a little calculator. This is 8 and 1, which is 9, but you could also scroll up and get that. This is 1111, which is 8 and 4 and 2 and 1. Although the way that I would do it is 4 bits, 2 to the fourth is 16. But if they're all ones, it'll be one less than that. So it'll be 15, if that makes sense. So like 111 is 7 because it's 2 to the 3, 3 bits, 2 to the 3 minus 1. So the biggest number you can represent with 4 bits is 2 to the fourth minus 1, right? So like if you wanted to know like what is this? 11111, right? All you would do is count them and see that there's 6. So it'd be 2 to the 6th, whatever that is, and then minus 1. And I guess the AI built into the Notes app knows that that's 63. Um, cool. Now we did go over converting to binary by we had a method of doing this seen on a t-shirt. Yeah, this is a very, very old joke now. Um, and for some reason people still say it, right? 10 kinds of people in the world, those who get binary and those who don't. Um, yep, right, because 10 is 2. So there's 2 kinds of people in the world. That's the thing. Awesome. All right, truth tables. I think we're just about at the end here. We've done truth tables. So, you know what? I'm not really going to do much here. So here's a truth table. If we're filling this out, we fill them out in binary number order, right? 0, 0, 0, 1, 1, 0, 1, 1. So that's 0, 1, 2, 3 as binary numbers. This one is also filled out in terms of binary numbers. 0, 0, 0 is 0. 0, 0, 1 is 1. 0, 1, 0 is 2. 0, 1, 1 is 3, 4, 5, 6, 7. Okay. So if we filled them out in that order, what would the J be? Well, this would be 0, 0, and this would be 0, 1, right? So the J would be 1. What would the K be? Well, it'd be 0, 0, 0, 1. So the K would be 0. What would the L be? Well, it'd be 0, 0, 0, 1, 1, 0, 1, 1. So the L would be 1. 0, 0 corresponds to what min term? Well, 0, 0 is not A, not B. 1, 0 would be A, not B. Function A, not B is to be represented in the table. So A, not B is 1, 0, right? A, not B is 1, 0. So if you were trying to represent this function, you would find the A not B is 1, 0. So you'd find the 1, 0 row and you'd fill that in with a 1. So we've done this already, actually, just not with the like M1, M2 kind of notation. So if the function was A not B is represented, what would M be? Well, if this was your function, you would find the spot corresponding to A not B and fill it in with a 1. Every other row would be 0. So if this one is a 1, then all the rest would be zeros, including M. The function of A, B, C, D, E has 5 variables. How many rows should it have? Well, it's 2 to the power whatever number of variables you have. So if you had 5 variables, it'd be 2 to the fifth, which is 32 rows. All right. We have done this. So you can go from the truth table to the equation. And from the equation, like there's an and an and. So there's two ands. They're separate. They're combined with an or. So there's an or. Um, Not A is A through a not gate. BC is just BC. AB is just AB. Not C is C through a not gate. Um, these three are ANDed, so they go through an AND gate. These three are ANDed, so they go through an AND gate, and so on. So let's do this real quick. What min term is row A? So 0, 1. So 0 for E is not E. 1 for F is just F. Row B, 1, 1 would be EF. Y is, so the, like, what function is this? So Y is going to be whichever ones are marked. So 0, 1 is not EF. And the last row is 1, 1, which is EF. So where the ones are, that's the terms you have in your function. Okay. An equation will be blank plus blank. So what's the first blank with A and B here? We're here, 0, 1. So that's not A, B right here. The second term is right here. This is A not B. That's here. Considering Y's equation, how many AND gates will exist? Well, with two ones, there's going to be two terms, right? These two terms. Two terms are going to be like this, right? Two terms means two AND gates. How many AND gates will, wait, wasn't it the same thing? Y's truth table. Oh, this is considering Y's equation, and this says considering Y's truth table. I mean, they're the same, right? A three input function whose truth table has 5 ones. How many AND gates will exist? Well, if you had 5 ones, there'd be 5 AND gates, right? Every term is an AND gate. Like this has 1, 2, 3 ones in here. So 3 terms here. So 3 AND gates. Um, all right. Let's do maybe 1 or 2 of these and stop. Feel like we've been going for a while. So convert the truth table to sum of min terms form. Okay, this has 1, 1. And it's from the row 1, 0, which is A not B. A not B. Skip to the third. This one has also 1, 1. And it's from this term. So this term is not A, B, C. Not A, B, C. Let's jump to the fifth. This has 1, 2, 3 terms. So we have 3 terms here. So the top, this one corresponds to 0, 1, 1. which is not A, B, C. The next one is 100, 100, which is A, not B, not C. A, not B, not C. And then the third one is 101, which is A, not B, C. A, not B, C. Cool. All right. We're still not done. Jeez. Well, we may as well finish this. I feel like we've got to be close, right? Uh, product of sums. So we don't really use this, but sums, right, are going to be like this is we did sum the products before. This would be a product of sums, right? Each individual term here is a sum, and they're a product of those. So is ABC a sum? No, that's a product. Is A plus not B a sum? Yeah. Is A not B plus C a sum? No, it's a mix, right? Product and sums. Is this a product of sums? Yes. Is this a product of sums? Yes. Is this a product of sums? No, this is a sum of products. So backwards. So you can see a max term is a sum that has all the function variables exactly once, but it's a sum. So instead of a product. Cool. So this is kind of going to be like the opposite of what we did for product of sums. So if you look here, here's a truth table. Notice that they are now labeling this instead of calling the 0, 0 row like M0, and then that's like 0, 0, which is uh not A, not B, right? That's what we were doing before. Now they're saying M0 is when those are zeros, will be actually, what are they doing? So a max term is a sum that has all the functions. Product of max terms is a canonical form where the right side expression is a product of sums. Um, each row of the truth table corresponds to a max term. A max term joins inputs by or, whereby an input of 0 that appears in the true form and the input that is 1 appears in the complemented form. So here, 0, 0 for the min terms is not A, not B. 0, 0 for the max terms is A plus B. So they're added and they're not complemented. Weird, right? Um, and so everything is backwards. It's sum instead of product, and zeros now correspond to the term without the complement, whereas zeros previously corresponded to the term uh, with the complement. So interesting, hard to keep separate, but we'll try to figure it out. So A, B, C, and then if it's a max term, that means none of the variables can be left out, and it's got to be a sum. So not A, not B, not C. Is that a max term? Yeah, I guess so. Is A, B plus C a max term? No, right? That's like a mix of product and sum. Is this a product of max terms? We have an ABC and an ABC. Yeah, I think so. Is this A plus not B, A plus not B plus not C? No, because this first one is missing the C, right? So we're not allowed to be missing the C. Is this a product of max terms? Yeah, I guess so. All right. How do you convert? Well, you can just multiply it all out, right? So if you had this product of sums form, you could FOIL it all out, distribute, distribute. So that's like FOIL. And then once you FOIL it all out, some of the terms will disappear. Like A and not A is automatically zero. B and not B is automatically zero. And it would just leave you with two terms. So that'll be easy. So like, what would you do here for this one? Not A plus B, A plus C. That's actually, so it's a product of sums. This is not a product of max terms actually though, right? Because not max terms. So what would you do? You'd FOIL, right? So you'd have not A times A, not A. Then you'd have not A, C. Then you'd have BA, which I'll write as AB. And then you'd have BC, which you write as BC. But then uh, not A and A is automatically zero. So this is just zero. So it'll drop off and we'll just have what's left, which is looks like this one down here. All right. So there's not too much there. Um, let's see what we can do with this. So write F's equation. Write F in chat if this is boring. Okay, so write F's equation for the truth table. So we have a term here. Actually, we need to do the zeros, right? So look up here, right? Where the zeros were in the function are where we got the terms at the end, not where the ones are, right? Where the zeros are. So when we're doing this, we need this term up here where the zeros are, which is 0, 0, 0, which would mean, oh, I gotta hit start. 0, 0 would mean, I think, A plus B. For this one, the 0, 0 up here means A plus B. And it's a product of sums. So we find the other zero down here, and here it's 1, 1, and the ones correspond to not. So not A plus not B. Okay, now we're done. So this is the entire end of the chapter. So I'm going to go ahead and stop this right here and talk to you guys later.